Sorry?
Just a minute.
Live streaming is started soon. Hello.
Hello, is there a problem or?
Devendra, is there a problem?
No, now it is okay.
Okay, please go on.
Okay. Yes. So maybe I should just briefly, before I start, say something about myself. So it might be interesting because I mean, Harishchandra was physics trained, as we just discussed, and then became a renowned mathematician. Now it's kind of funny because I'm physics trained myself, and previously I was sort of the mathematician in the physics department, and nowadays I'm more like the physicist in the math department. And what I will talk about is really at the interface between physics and math, which is what I find extremely exciting when we can ask questions about, nature, and we realize that we need math to answer them. And sometimes we even get pointed to sort of new math, and we can try to prove conjectures that come up in physics, and then also hopefully get some new physics insights. So I will talk about this kind of interplay mainly in the context of automorphic forms and its relation to amplitudes, in particular in string theory. So I understand that the audience is varied. So I will focus a lot on the math, but I will make remarks on interpretations in physics, and that may or may not be understandable, but hopefully it will be a little bit inspiring and could prompt people to go and look deeper. So let me give you a brief outline. So I will start with some motivation, talk about where these things come up in physics, these kind of automorphic forms. And I will be very brief here. I understand that there have been other talks in this series, but I will not assume that people know this. It will be more of a overview and just some pointers. Then the main two parts of this talk will be focusing on what are automorphic forms, how can we think of them from a representation theory perspective, which is of course where we think of sort of Harishchandra's legacy being to a large extent. Then I will point to some specific types of representations that we call small, and they are interesting both from a physics perspective and a math perspective. So hopefully I will give you a sense of that. And then I will end with some outlook. So this is the plan for the talk of today. Towards the end, I will mention something about what I plan to do tomorrow. So before I start, I just want to say something about where you can go to read more. So a few years ago, with some collaborators, we wrote a book where we really tried to give the full mathematical machinery and explain how it fits into string theory. So this was published in 2008. So if you want to have details of what I'm saying, then a lot of it is in that book. And then actually recently we wrote a short survey, which is very brief, but gives sort of the big picture of this story. So that's just finished from the proceedings of a number theory workshop. I want to say something about also, there are many, many people who have contributed to this field. I'm just listing them here. Some of them are my collaborators, some are friends, people I discuss with, and so on. So I'm just putting that out there. And then as we go along, I will, of course, present references where appropriate, but you can find a list here of people who are contributing to this field. Okay, so let me just jump right in. So to start with some motivation, I just want to stress that since I will be talking a lot about Fourier coefficients, they are important both in physics and math from many different points of view. So first of all, there is sort of the classical perspective of modular forms, where we know that Fourier coefficients encode number theoretic information, such as points on elliptic curves and so on. In the context of moonshine, which is a different exciting connection between math and physics that I also worked a lot on, but I won't really focus on today. There we have a close relationship between representations of sporadic groups and Fourier coefficients of modular forms. Maybe more relevant to this talk is if we look at higher rank groups, we have the full machinery of the Langlands program, where, of course, automorphic L functions and so on are closely related to Fourier coefficients of automorphic forms. And just to mention one of the previous talks, Sol Friedberg talked about the Langlands program in some overview of the Langlands program earlier this spring. And the main point for this talk is that when we focus on a particular type of automorphic form, namely Eisenstein series, they are relevant for certain amplitudes in string theory. And that's where most of these two talks will be based. So to set the stage for that, I want to start with just a few slides, talk about what we mean by an amplitude in quantum field theory and in string theory, and then go from there to how automorphic forms appear. So just at the very high level, if you want to understand something about how particles scatter in quantum field theory, you can think of two particles hit each other and going away, maybe new particles are created and so on. We talk about the probability of such a process happening being described by an amplitude. I've just given an example here of, say, a function of some 4 variables, P1, P2, P3, P4, and that's supposed to indicate 4 particles interacting in some way, and that's some complex number. So usually we depict these in a diagram, so time goes upwards here. So in particular, if you look at the middle picture here, it could be 2 electrons going in, interacting again, so you have a total of 4 particles. And the wiggly line in the middle represents the interchange of a photon. So it could be an interaction of this type that we call a 4-point interaction. On the very right, you have a similar situation, but there's just this big blob. I'm not telling you what's happening inside, but it could be some complicated process happening. So you can calculate this in quantum field theory, depending on which theory you're looking at, for example, quantum electrodynamics. And usually the way you do it is you do it in perturbation theory, which means mathematically that you have some small parameter called the coupling, and you expand your amplitude as a series expansion in this coupling. Now, it usually happens that you don't capture everything by just doing an expansion, power expansion in this parameter, but you usually have what we call non-perturbative terms. And I've indicated here that they could go like e to the minus 1 over the coupling, so they will be exponentially suppressed. So it's something you can sometimes calculate. But the main point of this talk is not really in quantum field theory, but I want to talk about the similar story in string theory, which is a huge topic in itself. But I want to be extremely broad here. And the way you can think of, instead of having a point particle, so if you look at the middle diagram here, you can think of this as 2 sort of electrons, which are like point particles moving in time. When you have a string, this is like a one-dimensional object that is extended. And what happens then if you have a closed string moving, it traces out a surface in space-time. And so the typical 4-point interaction of, in this case, gravitational particles looks like what you see on the left part of this screen here. It's usually called the pair of pants diagram. So you have like 2 strings coming in, they interact somehow and go away again. And this is what makes it quite distinct from the situation in quantum field theory, because you have this surface where the interaction takes place. So you can really do a conformal transformation and present this as a Riemann surface with some marked points. And that's what we do in when we do calculations with this type of process. But the picture here is also indicating that you can have a similar perturbative expansion that was similar to what I had on the screen before, but the coupling now is really related to the topology of this world sheet. So you see in the middle here we have a hole in the surface, so that's a genus 1 diagram. Then you can go to genus 2, and so on and so forth. So this expansion is actually an expansion in the genus of this world sheet. So that's a new feature that you have in string theory. Another aspect is that there is actually a 2-parameter expansion. For historical reasons, the other parameter is called alpha prime. You can think of this as sort of the size of the string, if you want. A little bit later, I will show you more explicitly what that parameter expansion looks like. But for the purpose of just this slide, we have this 2-dimensional space of parameter space where the genus expansion is on the y-axis and this other expansion is on the x-axis. I've given some zeta functions down there, zeta 3 and zeta 5. In a moment, I will explain to you where those come from. But for the moment, I'm just putting them there for later use. Now, the amazing thing is that when you do this, when you try to calculate these amplitudes in string theory, there are some very constraining symmetries. In particular, there is something called supersymmetry, which is an exchange of different types of particles, bosons and fermions. And there is a symmetry called U-duality, which boils down to an arithmetic structure in these amplitudes that is given by essentially saying that they are invariant under a certain arithmetic group. And so when you take these together, they have a strong constraining. So they constrain these amplitudes a lot, and you can use it to learn many things. In particular, you can learn about non-perturbative effects. I mentioned briefly before that you have these effects in amplitudes. In string theory, they could be interpreted as black holes or instantons. But we could also use them to extract novel mathematical predictions, or we can use what's known in math to extract physical insights. So this is the kind of interaction that I'm interested in this talk. So for now, I want to focus on this arithmetic structure a little bit. So there is this famous series of symmetries that you have. So one curious feature of string theory is, as you might have heard, is that it naturally lives in 10 dimensions. What you can do, so we are used to hearing that our world is 4-dimensional. And so what you can do in string theory is to try to compactify space-time into something lower dimensional. So what I've listed here is what happens if you compactify your 10-dimensional theory on a circle, a torus, a 3-torus, and so on, going down to lower and lower dimensions. So what happens is that the symmetry group of string theory becomes larger and larger. So we have this in 10 dimensions. There is an SL2R symmetry. When you go down to 9, you get an SL2R cross R plus symmetry. Go to 8 dimensions, you get an SL3 factor as well, and so on and so forth. In addition, we have a symmetry under sort of local symmetry that is the maximal compact subgroup of G. So for SL2R, this is given by special orthogonal group SO2. But in addition, there is this thing that is called S-duality. That is a statement that in the full quantum theory, the symmetry that is preserved is the arithmetic subgroup. So in SL2R, it's the SL2Z subgroup. And as we go down, all the way down to 3 dimensions, we have E8 of R as the classical symmetry, but this is broken to the integer points of E8. So what this means in practice is that when we calculate amplitudes, they are effectively given by functions on this arithmetic quotient. So you would have the symmetric space G mod K, but in addition, you have a quotient by the discrete subgroup. So this is the start of studying sort of the arithmetic properties of these functions. So far, we don't really know that these are automorphic functions. I will talk about this more in a second, but I want to make a brief remark that the way we usually think about it and the way I will talk about it in this talk is that when you calculate an amplitude, that is something that you feed into an action functional. So usually in theoretical physics, when you formulate a theory, you do it in terms of a functional of all the physical fields, and the critical points of that functional gives you the equations of motion of the theory. And so to give an example that is relevant here is that Einstein's equations in 4 dimensions, they can be derived by looking at the functional of the metric tensor, that's G, and R here is the Ricci scalar in differential geometry. So this is a functional from which you can derive Einstein's equations. Now, even if you don't know how that works, the point I want to make here is that what string theory does, it doesn't produce precisely Einstein-Hilbert gravity. It produces Einstein-Hilbert gravity in 10 dimensions plus corrections. And those corrections present themselves as extra terms in the action. So I'm schematically listing here the first few corrections that you can find in string theory. So I've given you this in 10 minus n dimensions, depending on which compactification torus we choose. R to the 4 here denotes a certain combination of 4 Riemann tensors. You see the alpha prime here to the cubed, alpha prime to the 5. This is indicating this x-axis part of the expansion. So you can expand this into to infinity as a power series in alpha prime. And you see that what happens is that you go from R to the 4, and then you have derivatives, 4 derivatives to R to the 4, and so on. So you can sort of think of this as a derivative expansion. But for our purposes, I want to then come back to this diagram and think about the y-axis. So each of these functions that are coefficients here, so I'm calling it f0 of g, f4 of g, they are supposed to contain the entire genus expansion. So this is an expansion in principle to infinite order of the genus of the world sheet. Now, the remarkable thing is that we can use these symmetries to say something about these functions. So that's what I want to address next. What we know is that they are functions on this symmetric space. I'm denoting these symmetry groups by En plus 1 of R, depending on which torus we're compactifying on. Now we know that the functions must be invariant under this symmetry, the discrete subgroup of En plus 1. Moreover, you have this other symmetry called supersymmetry. You can show that this gives you a differential equation condition on these functions, so they must in fact be Laplacian eigenfunctions. And they should have a well-defined expansion as GS goes to 0. Now, essentially, these conditions are the defining properties of an automorphic form, actually going back to Harishchandra. I will give the formal definition in a moment, but you can really see that step by step, by just looking at the constraints from string theory, you deduce that these functions must be some type of automorphic form.
Sorry, can I just interrupt with a question?
Yep.
Small clarification here. So this is for me mostly familiar, but I just wanted to be a little clear about this Laplacian eigenfunction. So could you maybe it's slightly off the main point, but could you just say why supersymmetry determines that they are Laplacian eigenfunctions?
So this is work of Green and Sethi originally. I should have put a reference there. So this is when you act on this function with the supersymmetry generator and you want to prove that this is supersymmetric, you will see that you actually get certain conditions on these functions so that the actually supersymmetry generator will give you a differential equation for these F0. So it's sort of a technical analysis that shows you that you get differential equations for supersymmetry to hold at each level.
I mean, naively, thank you. I mean, naively, I would have said the supersymmetry just takes us to a fermionic partners of these terms, right? So maybe you have to apply it many times to get.
Yeah, you have to apply. So in you get this whole, you get the whole super multiplet, but you can't get the whole multiplet without having certain conditions on F0.
I see. Thank you.
Yep. Good. So I want to give an example. So I want to spend quite some time on sort of the simplest example, which is this is mainly for the mathematicians to see sort of where this how we interpret sort of familiar objects in math from a physics perspective. So I'm going to assume that I am just up in 10 dimensions. I have this function F0. Now, what happens in this case is that this function here is what we say a function on the moduli space of string theory. I'm calling the parameter tau here. This is naturally comes out of string theory that this is parameterizing the upper half plane SL2R mod SO2. In physics lingo, we call it the axiodilaton. It doesn't really matter from a math perspective. But we require that this function must be invariant under Möbius transformations under SL2Z. That's what we call S-duality. So that's first constraint. Then we have the constraint from the Laplacian, and it's actually not just any eigenfunction. It's an eigenfunction with a very specific eigenvalue. So that's a constraint that comes out. And moreover, we do know that when we expand it to lowest order in the parameter y, which is in the physics lingo, this is the inverse of the string coupling. So then it's actually has a coefficient which is 2 zeta of 3 y to the 3 halves. So that's the leading order correction from a string theory point of view.
Sorry, if I could just bother you again.
No.
Oh, maybe you're, I think I got my answer. I was going to ask if these Fs are holomorphic functions of tau, but clearly they're not.
Very good. So I will get to that. They are not holomorphic functions. It's maybe I'm cheating when I just write tau, but they are not holomorphic. Thank you.
Okay, thanks.
So you can find that there is a unique solution to these conditions, which is given by this double sum over two integers. So this was first pointed out by Green-Gutperle. Green-Sethi continued the analysis. And also Piolin later confirmed, because there is, as I might mention later, there is this slight question here if there could be other so-called cusp forms contributing that would not spoil the leading behavior in the limit, but there are actually no cusp forms in this situation. Okay, so that's it. So let's see, what kind of object do we see here? Well, consider the following sum. So this is a sum over two integers c and d that are required to be co-prime. So this is the form of a well-known object. It's the non-holomorphic Eisenstein series defined for a complex parameter S. It's a function on the upper half plane. It's invariant under Möbius transformations. It converges absolutely for a real part of S sufficiently large. It's an eigenfunction of the Laplacian with this particular eigenvalue. Actually, you can go ahead and prove that it has an analytic continuation to the full complex plane. Now, for our purposes, we are mainly interested in looking at the expansion of this function with respect to the periodicity that you have when tau goes to tau plus 1. So, of course, the invariance under SL2Z, I should have written SL2Z here, ensures that when you shift tau goes to tau plus 1, this stays invariant, so you do have a Fourier expansion. So the Fourier expansion looks like this. Now, as Sunil was asking about the holomorphic property, if this would have been a holomorphic modular form, we could have written the Fourier expansion completely in terms of the Q, so 2 pi e to the 2 pi I n, and then x plus I y. That's not possible here, so you can expand with respect to the Fourier mode is like the real part of tau, but then you have some coefficients that depend on the imaginary part of tau, f and y. So that's what we call the non-zero mode, and the constant term is the zero mode in the Fourier expansion. So you can go ahead and do this explicitly, and so what you find for the constant term is these two terms here, y to the s. Then you get a ratio of completed zeta functions and y to the 1 minus s. For the non-zero mode, you get a Bessel function, a modified Bessel function type k with order s minus a half. As a coefficient here, you have a divisor sum over the divisors of n. So this is a well-known Fourier expansion of this non-holomorphic Eisenstein series. So I want to now reinterpret this from a physics perspective. So if we look at this function es of tau, so what I'm going to do now is, I should have written this explicitly, but I'm going to rescale this slightly. So the f0 that I wrote before, it's a rescaling of this e. So I forgot to put that on the slide. I'm sorry. So you see here that this has a constant term starts with y to the s, but a rescaling of this es gives you exactly the structure that we had in the object appearing in physics. So we have a 2 zeta of 3 factor, y to the 3 halves. That is interpreted in string theory as the leading term corresponding to the diagram with no holes in it. The second term that you get from the Fourier expansion has a coefficient 4 zeta of 2, y to the minus a half, and that has a natural interpretation as the one loop correction to this leading result. And then you have an infinite series of coefficients that are given by, so I just wanted to also, again, just remind you that this 2 zeta of 3 was exactly the first term that I gave in this. Now, what is quite interesting here is that in principle, as you see in the diagram, we could have an infinite series of higher genus corrections. But what happens here is that actually this automorphic form, this Eisenstein series, has only two constant terms. There is a tree level and a one loop term, and there are no other powers of y in this setting. So that's a constraint telling us that, in fact, this particular part of the effective action cannot have any higher order loop corrections. So that's a constraint from this automorphic symmetry. You also have a term that goes to the e to the minus s inst. That's what we in physics call the instant on action. This is just expanding the modified Bessel function k. And what you get here is something that goes like e to the minus 1 over the string coupling, because you see here that the y parameter in the instant on action is 1 over the string coupling. So this is the type of effect that is exponentially suppressed. So I think I also accidentally changed notation here. So I'm calling this divisor sum sigma. In the previous slide, I called it mu. I apologize. It's the same object. It's just that this is now a particular value of S. So to summarize, just go back here. What we have seen is that the function that appears in string theory here is this non-holomorphic Eisenstein series evaluated at S equal to 3/2 with the particular normalization. So the conclusion here is that in this setting, you have Fourier coefficients of this automorphic form encoding information about scattering amplitudes in both perturbative and these kind of instanton effects. So it's a very powerful result, and it comes more or less completely by using these kind of strong symmetries that we have. So a lot of the work that has been going on since is to try to understand how this generalizes to higher rank groups, other types of Fourier coefficients, and so on and so forth. So maybe this is a good time to ask if there are any questions, confusions. Crystal clear. That's perfect. So I want to use this now as motivation to go into a more general setting. So let's think about a Lie group, a real Lie group G of R, and some arithmetic subgroup G of Z. You can just think of this as SLN-R if you want, and the discrete subgroup is SLN-Z. And we have this definition. So an automorphic form is a smooth function on G that satisfies the condition of automorphy, namely invariant, under the discrete subgroup. This is acting with gamma. It should be an eigenfunction of the entire ring of invariant differential operators on G, not just the Laplacian, but for higher rank groups, you have higher order Casimir, if you want, in physics lingo. And it should have some well-behaved growth conditions. Actually, I should be more specific and put in a condition on how it behaves under the maximal compact subgroup as well. I will mainly be interested in functions that are just invariant under K, so that simplifies life a little bit. But there is a condition that is usually called K finiteness, that they generate a finite dimensional representation of K. So this is a definition that I think was first essentially written by Harishchandra. And for our point of view, we want to look at a generalization of the Eisenstein series that we had. So I want to look at specific types of automorphic forms that generalize the non-holomorphic Eisenstein series I had before. And so I'm going to use the definition due to Langlands. So this is an Eisenstein series that you get by taking a group. I'm taking a group G of R, and I'm defining it as this sum over integer points of G quotient on the left by the Borel subgroup. So what does this mean? Well, first of all, I'm assuming that the group here has an Iwasawa decomposition, so it can be decomposed into NAK, where NA together is a Borel subgroup and K is the maximal compact subgroup. So feel free to think of this as A being the diagonal matrices and N being the upper triangular matrices with ones on the diagonal. And then what we have here is in the summand, you have capital H is what's usually known as the logarithm map. It's like a map from the group to the Cartan subalgebra of the Lie algebra. So I'm going to assume some Lie theory here, but we take the Cartan subalgebra is the Lie algebra of the diagonal matrices, if you will. Then H acts on an Iwasawa decomposed element by taking the logarithm of the A element like that. We have the weight lambda. That's you can think of it as a complexified weight of the Lie algebra. In the example we had before, that corresponded to actually the parameter S. More generally, this is really a function of the entire complexified weight space of the Lie algebra. And finally, rho here is the Weil vector, is the half the sum of the positive roots of the Lie algebra. So this is kind of a lot to take in, but I just want to, some more properties before I give an example. So there's a condition on convergence. Before we had the convergence, like the real part of S was sufficiently large. Now it's also something called Godemon's domain, where this converges. And it's a famous result of Langlands. Well, it proved in more generality that you can continue this to a meromorphic function on the entire complexified weight space. It is invariant under this arithmetic subgroup on the left. It is invariant under the maximal compact subgroup on the right. It's an eigenfunction of the Laplacian with a specific eigenvalue, and it satisfies a functional relation like this. So these are known properties of this Eisenstein series that you can find in Langland's 270-page manuscript. It's not so easy to read. But just for this purpose here, it's useful to just look back at our example. So for the object that we talked about before, the SL2R Eisenstein series, you can quite easily see that this reduces to that expression if you pick lambda plus rho is 2s times capital lambda. Capital lambda is the fundamental weight of the simple root of SL2. Then the action of this logarithm map will just amount to y times h alpha, where h alpha is the Cartan generator corresponding to the simple root. And then you take the pairing of the weight and the Cartan element. In this case, it's just 1 because lambda is the fundamental weight. And then you have to analyze the sum over SL2Z mod B of Z, and you can see that this is sum over two co-prime integers. So then this general expression reduces to the familiar one. Yes, so that's how we construct an Eisenstein series that generalizes the object that we saw before. But how do we think of this from a representation theoretic viewpoint? So that turns out to be extremely useful. So I'm just going to have to say some words about how to think of this in this abstract way. So these Eisenstein series constructed by Langlands, you can associate them to the principal series of the Lie group. So what do we mean by that? This is the function space corresponding to functions on G that transform on the left by an action of the Borel in terms of a multiplication by a character chi. Now, I should have written it, but chi here is really, you can really construct it from this kind of exponential expression that I have here. So this summand is like the character on the Borel extended to the group G. So that's where this chi comes from. And you define a map from this representation space into the space of automorphic forms. Now, the space of automorphic forms is a beast that I'm not going to try to really analyze, but the whole idea is that you do have some representation of the group, and you can realize it inside the space of automorphic forms as this Eisenstein series. And it's a big point here that this is preserved by the action of G. So you can act with the group on these functions by the right regular action. So f of G, you can act with the group by just translating the element G on the right. And that doesn't change the invariance properties on the left. So you preserve the space of automorphic forms, and you can really ask about decomposing this action into irreducible constituents. And those irreps are essentially what is called automorphic representations. I'm skipping a lot of technicalities here, but somehow I think this is the moral of the whole thing. I want to give one toy model here that I find useful. And we can sort of think of Fourier analysis on the circle, just to have an idea of where we're going. So if we look at functions like this, you can, of course, you have a periodicity, so you can decompose functions like this into Fourier modes, where Fourier modes are like functions from R mod Z into U1. So you can just realize them as e to the 2 pi I kx, where k is an integer, x is a real number. And if we look now, so this is like the automorphic condition. And I said also, well, we should have some kind of growth condition. We can do that by restricting to square integrable functions. So we add this condition. And then the group G, which is just R in this case, will act via the right regular representation, which will be shifts of x by a real number y. And, well, if you decompose this, you will decompose it into Fourier modes, which is like, in this case, sort of automorphic representations. So this is one way to sort of get a feeling for what you might mean by an automorphic representation in a simple toy model situation. Now, one very useful concept. So these are, of course, infinite dimensional function spaces. So it's different from when we talk about, let's say, finite dimensional representations in quantum mechanics or something like that. But there is a very useful notion of size of an automorphic representation, and it's called the Gelfand-Kirillov dimension. So roughly, it is like the smallest number of variables on which the functions can depend, roughly. So as an example, if we look at square integrable functions on Rn, the Gelfand-Kirillov dimension would be just n. We realize them as functions of n variables. For the principal series, the Gelfand-Kirillov dimension, it's like the dimension of G mod the Borel, which is also the dimension of the upper triangular matrices known as the unipotent radical. So I'm stressing this because in the physical interpretation, you have sort of a rough correspondence that actually the Gelfand-Kirillov dimension is related to the number of independent physical charges. So in the SL2 example that we had before, well, there is this sort of, well, the Gelfand-Kirillov dimension of the principal series is just the dimension of the upper triangular matrices with just one entry. So that's one dimensional. And also in the Fourier sum, the sum over instant on charge is just one dimensional. So it's sort of a simple realization, but it holds more generally. So this concludes my general discussion of automorphic forms and representation theory for now. And I want to go into how we think about Fourier coefficients in this more general setting. Remember, I started with the simple example of SL2, constructed the Fourier expansion. But as soon as you go to higher rank groups, things become much more complicated. I want to give an idea of how we do it. How am I doing for time? So there should be, what, 15 minutes left or?
Yeah, 15.
Okay. Yeah, a lot to cover in 15 minutes, as usual. Okay, so what do we mean by Fourier coefficients? Well, first of all, for SL2, I said, well, we have functions of tau. Tau shifts by 1. That's a Fourier expansion. When we look at the general case of an Eisenstein series, this amounts to the possibility of shifting the group element by an arbitrary integer or arithmetic upper triangular group. So that shows that, okay, there must be something like a Fourier expansion, but it's much more complicated because this n of z is non-abelian. It's not just a product of circles. So it's a non-abelian group. So what can we say about the Fourier expansion? Well, in general, we would expect there to be a constant term. That's what we call a zero mode. I forgot to mention, it's called a constant term. It's a bit of a misnomer because it's not constant. But in the case of just holomorphic modular forms, it is constant. So I guess it's a terminology that has survived, but it is not constant. Then we have the type of coefficients that I like to call abelian. This W psi are what mathematicians call Whittaker coefficients. I will discuss them in detail shortly. But the point here is that this is not all, because you have a whole series of what's known as non-abelian coefficients, and I will mention a little bit later what is the distinction between them. From a physics point of view, these all capture various non-perturbative effects. So for now, I want to go in and talk a little bit about this W psi. What is the structure of that? Because it will be the main star in what follows. So W psi is what's known as a Whittaker coefficient. So what is it? You can define it in this way. So it's an integral over the sort of fundamental domain for the action of n of z, n of r. So it's the coset n of r over n of z. So it's a compact quotient. It's the Eisenstein series in the integral, in the integrand, and it's shifted g by n. And then you have psi with a bar on top. So that's the analog of the Fourier mode. So what is this psi? It's a function from n of r to u1, but it's required to be trivial on n of z. Just so you can sort of think of it as the analog of e to the 2 pi I nx. And it's what's to call a unitary character on the group n, trivial on n of z. So concretely, you can realize this as this in the same way. If you introduce a set of simple roots of the Lie algebra, then you have sort of the Fourier modes are integers mj, and the parameters are real numbers xj. And so that's how you would parameterize this more general character. For SL2, you just have one term in this sum, m times x. So some terminology here is that if all of the coefficients mj are non-vanishing, then you call psi a generic character. And if some of them vanish, then psi is called degenerate. So that's what this is. Now, let me give some examples to sort of connect back to what we have seen before. Suppose we would have a holomorphic modular form. Then well, as I said before, the character psi would be just e to the 2 pi I mx. And if psi is generic, then m is non-zero. So it's basically saying that psi is non-trivial. The integral here, well, n of r over n of z, that you can think of just as the integral from 0 to 1. It's like a fundamental domain for this quotient. And then you just have the function f. You act with n corresponds to tau plus 1. If you perform this integral, then you get just the Fourier mode, which is like q e to the 2 pi I m tau, is like the q expansion of a modular form. And then c of m are some rational numbers. That's what happens for a holomorphic modular form. Another example, which is the one we talked about, this non-holomorphic Eisenstein series, if you would calculate this integral in that case, well, you get precisely the Fourier modes that we talked about before, where it's not just the numerical coefficient Cm or just rational numbers, but in this case, you get the full non-trivial dependence of the y parameter in terms of a modified Bessel function and some divisor sum in front. So that's connecting back again to something more explicit, but this all comes from the definition of a Whittaker coefficient. So one thing that I want to mention is that when you look in the math literature, you very often see them discussing how this kind of coefficients can factorize. So I think we all are familiar with the fact that the Riemann zeta function can factorize into a product of prime numbers. Now there is a generalization of that actually this coefficient here, you can think of it as factorizing into an infinite product over primes. Then there is a prime at infinity called the Archimedean prime, and the coefficient containing the Bessel function that can be interpreted as coming from a prime at infinity, while all of the finite primes, they correspond to sort of p-adic contributions to the Fourier coefficient. So if you actually evaluate this product over primes, then you will reproduce the divisor sum that I had before. So this is a bit technical, but I want to say this because this is the basis for what's known as the adelic formulation of automorphic forms, which is a big part of the literature is using, and it's very powerful. And it took us a long time to absorb it, but I mean, Langlands has a nice quote where he says that an efficient but abstract way to approach the subject of automorphic forms is by the introduction of adels. They are rather ungainly objects that nevertheless, once familiar, spare much unnecessary thought and many useless calculations. And after having delved into this, I can only agree that it provides a very powerful framework. So roughly speaking, what you want to do is you start with sort of the Eisenstein series that you are interested in, maybe more familiar over the real group over the real numbers. You can lift this to an adelic Eisenstein series, and you make your computations in this setting, and then you can restrict back down to what you're interested in. So in this book that I mentioned, we try to do this very, very explicitly, mainly for the purpose of students and physicists who want to get a handle of this, how it actually works in practice. Now, for this talk, I don't really want to go into the details here because I think it's taking us a bit too long. So I just want to say, because I will use, from now on, I will use this notation, but you can just ignore it if you want. But the idea is that the group G of R is replaced by a group over the Adel points, and the group G of Z is replaced by the group over rational points, because rational points sits inside the Adels. So everything has an analog in the adelic setting, and you can just ignore it if you want, or you recognize it. So I'm just mentioning it here. Okay. So there is some extremely powerful theorem about these Whittaker functions. So when psi is generic, it is known that in general, so let me just go back to remind you. Sorry about this. Look at this Whittaker function I have in the definition. So this, in the integrand, you have the full Eisenstein series. So remember, this is a sum over G of Z mod B of Z. So it's a complicated sum inside. Now, the way to use, to compute this is that you sort of unfold the sum against the integral. You can use the Bruja decomposition to replace this by a sum over the Weil group. And actually, at the end of the day, what you find is that there is a single contribution to this sum. There's only one element of the Weil group that survives, and that's the W0 is the longest element of the Weil group. So this entire sum, there is only one term remaining. So this is quite an amazing simplification. And this also shows that this integral is actually Eulerian. It has a product factorization. And you can treat these as separate integrals. So you have an ordinary integral over n of r, which is called the Archimedean. And then you have an integral over the p-adic one. And I'm not going to go into details of how to calculate this p-adic one, but I want to say that there is this amazing theorem of Shintani for SLN, and then Kasselman-Shalaika more generally, that this Whittaker coefficient for each prime is actually given by the Weil character formula for the Langlands-Duan group. So here we see the role of the Langlands-Duan group as it comes in terms of how you understand the Fourier coefficients. So that's quite remarkable. In the book, we try to explain this in detail as well in some examples. So one thing I want to say, I'm getting close to the end, but I want to sort of set up some of the stuff for tomorrow. So I've talked completely about the Fourier expansion with respect to this upper triangular matrices that I call N. Now, if you think about it, that's a very special situation. If you go to a higher rank group, there are other unipotent matrices. This is like the biggest one, if you want. But you can have other simpler matrices. Let me take an example for SL3. So if we just do SL3, well, the unipotent radical of the Borel is just this once on the diagonal, and then you have these upper triangular elements. You can look at other unipotent groups. They correspond to other parabolic subgroups than the Borel. So in particular, these two are interesting. So you're just looking at elements that have non-vanishing in the top row or in the rightmost column. Now, you can talk about Fourier expansions with respect to these. And actually, from a string theory perspective, that is extremely natural. Because depending on which direction, so which unipotent group you are Fourier expanding with respect to, you extract different physical effects. So I've indicated this here in 3 different limits. There are string theory literature called decompactification limit, string perturbation limit, M-theory limit. They correspond to choosing different unipotent radicals. So I have given here the Dynkin diagram of E8. I hope 1, 2, 3, 4, 5, 6, 7, 8. Yes. I will talk more tomorrow about the role of exceptional groups. But I'm saying this because I want to now set up the discussion of, I want to sort of talk about Fourier coefficients with respect to more general unipotent groups, which is a big topic in math, and it's also relevant for string theory. So that's what I want to get to. But I think this is probably a good place to stop. And so for tomorrow, I want to talk a little bit about how to calculate Fourier coefficients of these more general parabolics or unipotents. I want to give a physical interpretation, and then I want to get to the small representations that this comes into string theory. So it's probably a good place to stop.
Good. Thanks very much, Daniel, for this very beautiful talk. I guess we need to attend the talk tomorrow to see where it all leads up to.
Yes.
You are speaking tomorrow?
Tomorrow I will just talk about something completely different.
But starting from here.
Yes, yes. I'm just kidding. So I will continue from here. And hopefully I will get to yeah, let's see where I get, but I know
minimal representations. So
yes,
minimal
yes.
representations have not come yet today.
They have not come yet, so they will come very, very soon. So tomorrow I will first discuss some aspects of general Fourier coefficients and then go to minimal representations. That's the plan for tomorrow.
Great. All right, so let's invite some questions if there are any. Anyone?
Is someone checking the YouTube live because maybe sometimes there are questions there.
Maybe Sunil has some questions to ask.
Yeah, it's I must say, I mean, I understood actually, probably you and I, Dipendra, understood complementary parts better because the setup was sort of reasonably clear of trying to understand these Fourier coefficients as string amplitude corrections. And after that, though, you know, when it came to the hard stuff about Langland's Eisenstein series, I've seen it before. I sort of see where it's going, but I don't think I would have any really intelligent question right now. Maybe tomorrow, though.
Mm-hmm. All right, good. Anyone else? If not, let's wait for tomorrow's lecture and think about more things which may be confusing us for today.
Yep.
So let's thank Daniel today for the beautiful talk. Thank you. All right, so
very good. So same time tomorrow.
Right. Yes.
Same time tomorrow.
Yeah. So thanks to speaker and the chairman also, Professor Dipendra Prasad, for good participation. Thank you.
All right. All right. So bye everyone. Looking forward to the next talk. Bye.
Bye.
Thank you. Bye-bye.
Bye. Bye.
Thank you.
Hello.